Yeah, so we are looking at wave equations, scattering for wave equations, nonlinear wave equations, and typically, schematically, a nonlinear wave equation can look like something like this. And the idea is that this equation, the nonlinear term, influences the behavior, so that if you want to do scattering, that is post data at infinity, then the solution is not going to behave like a solution of the linear wave equation, like you have 0 on the right-hand side, but there'll be some corrections at infinity, and in particular, in examples, it's proven, like for Einstein's equation, proven that you have a logarithmic correction to the behavior. And moreover, if you have compact spotted data, the solution will be 0 out here, but there's still going to be something in the interior that might look like 1 over t. For that is not there for linear equations. So you have to somehow take that into account and figure out what goes on in the interior. So the idea, if you follow if you're in relativity, you might have heard the name Penrose. And he posts data. If you follow Penrose, you want to post data at null infinity. That is when R is like t. But there is also something going on in the interior due to this right-hand side. So you have to somehow connect the data at null infinity to what in geometric scattering, Melrose looks at the problem in the interior. And you somehow have to connect those two things. And moreover, for equations like Einstein's equation and other physical equations, Maxwell's equation and so on, you have slowly decaying data. So you don't have compact support, but you have solutions that decay like 1 over r. By m of r by m has to be positive by the positive mass theorem. So then you also have to connect the solution in the exterior, the interior, and over the light cone at null infinity. So that's, first we are studying the forward problem for this, and then we want to study the problem where we give this kind of data at infinity. And an interesting thing that showed up here is that we studied a backward problem. In the exterior, we use something called the Funk transform. And this has a particular, Funk was actually a professor here in Vienna. He was born in Vienna, and then he got a PhD from Hilbert, and he eventually, after the war, came back and became a professor in Vienna instead. There's someone here who knew him. He died in 1969. He was professor at TU, Technical University in Tübingen. Yeah. Anyway, we will come back to that later on. Okay. So now I guess I can turn off the light now for a while. So you can point with this one, right? Is there a red thing on this? Or? Oh. Is it another one? This one. Okay, thank you. Yeah, so we will now study nonlinear wave equation with right-hand side. And then, we would like to give data at infinity and solve backwards. First, you have to study the forward problem and understand the detailed asymptotics for the forward problem. And there is something called, for solution of linear wave equation, when you have 0 on the right-hand side, there's something called the Friedlander radiation field, which says that the solution to linear wave equation looks like this, right? We all know that the waves decay when they spread out, so it decays like 1 over r or 1 over t. But moreover, so by some sort of Heisenberg principle, it becomes like a plane wave far out, right? So it looks like a function of r minus t, essentially, and much slower dependence on the angles. And this was proven by Friedlander, but there's something it involves the proof involves a Radon transform. There's an explicit formula, the Radon transform of initial data, but it can actually be proven in a simpler way, which I will explain because it also shows the limitations of when you. I mean, you want to prove this now. For Friedlander, prove it for compactly supported data if f is 0, but now we want to extend it to when f is slowly decaying and also data is slowly decaying. So I just want to show how you get that proof here. And then I need a light on again, I think. So can I just turn this one on maybe? No, the other one, this one. Yes. So if you write the wave equation in the spherical coordinates, this is the expression, right, for the wave operator. And then you integrate this up. And when you do, you will see that what you actually need for this limit to exist, it's exactly that it's integral in t plus r direction and in t minus r direction. So basically, what you do is that you take some point in here and you integrate back to initial data over this region in t plus r and t minus r, and then you get that r times phi is equal to the integral over this region. And you see exactly that for this integral to be finite, as this approaches infinity, you need exactly like that this should be integrable in t plus r direction and in t minus r direction. So you need a little bit more than power 1 here. This total decay with this r, power 2, and a little bit more than integrable epsilon positive in t minus r direction also. And similarly, you can also see that when you integrate from initial data here, that you need this decay initial data that decays faster than 1 over r. So it just misses the charge and the mass in relativity. Okay. Now, this assumed that you had some bound for the angular derivative. This argument is exactly in the spherical symmetric case. So to prove it in the non-spherical case, you need some bound for the angular derivative, but there's a lot of room for this because angular derivatives behaves much better for wave equation, essentially because of what we will prove. But you can get them from L2 estimate by commuting the wave operator with rotation operators and so on. So this is easy to get bound for. So then, yeah. But then the thing is that in general, for quadratic nonlinearities, it's not going to satisfy this bound that we want it to satisfy. For instance, if you look at, in fact, if you look at box phi equal to the t phi squared, Fritz John proved a long time ago that this one blows up. And we will see it's exactly because, it's exactly because we have something, if we know that phi decays like 1 over r, then this is just going to decay like 1 over r squared, which was exactly forbidden. On the other hand, Kleinemann showed that you have global existence for an equation that satisfies the null, so-called null condition. And what happens for the null condition? Well, if you plug in, assume what you want to prove, that you have this asymptotic, you see that this phi the t squared minus the r squared, this just cancels to highest order. It becomes, because you differentiate this function, you differentiate this function f, right? If you differentiate with respect to t, it's essentially the same as differentiating with respect to r, because if the r derivative falls on this, it decays much faster. So the slowest decay you get if you differentiate this factor, and then the t and the r are the same. And because of that, if something satisfies the null condition, you get something that decays better, which is allowed, right? With power bigger than 2. So then the asymptotic will be that of a linear wave equation. Now, there's something called, I mean, this may not be so interesting because this blows up, but there's something called a weak null condition that we discovered holds for Einstein's equation. in a null frame, and that's this system. If box phi is 0 and you plug it into the right-hand side, of course you're going to get global existence. But when you study this equation, you get the right-hand side that decays exactly like a function of 1 over r squared, which was forbidden. Well, you can't get the radiation field that way. So it behaves essentially like a function of r minus t divided by r squared. And that's for Einstein's equation. And also initial data decays like m over r. That was the other thing that was forbidden. And similar for, if you look at Maxwell's equation, this can be modeled by this system that also satisfies the weak null condition. In fact, it's a bit worse behaved as far as the semilinear term. And the right-hand side is also not decaying as much as we want. Okay. So we are led to studying this problem. So this is actually what we will study now. When we have a right-hand side, we sort of use the asymptotics for the nonlinear problem and plug it into the right-hand side. So we study this problem now, where you assume that this n has enough decay in the r minus t variable. That's what you get if you have a solution to the linear equation with sufficiently fast decaying initial data. Now, this doesn't work with radiation field, but from my work on Einstein's equation, asymptotics for Einstein's equation, I know that the solution should be sort of on this form. And then you plug that in to the wave equation, and you see that, well, the wave operator applied to this becomes much lower order, decays like 1 over r squared. But the leading term would be when the t minus the r falls on this factor and the t plus the r on that factor, and there'll be this factor. The derivative of this guy in front of the logarithm with respect to r minus t, and then everything else decays faster. And then you want to set that equal to the right-hand side. And you do that. And also you want to have compactly supported data, so you assume that this decays at infinity. So you get this formula for whatever the coefficient in front of the log has to be. I mean, this we can prove for the forward problem, but if you solve from infinity, you want to prescribe this. Okay. And in particular, this has a limit that is non-vanishing as you go to the interior, if this integral of n is non-vanishing. So it means that you get something in the interior that looks like 1 over t, or 1 over r actually in this case, because this has a limit as you go to the interior, which is like a function of omega. So, yeah. But there's another thing that you can see, which is that this radiation field is not, this part is not arbitrary. So this part is determined by the right-hand side. And this part comes from solving a linear equation. You can always add a solution to the homogeneous equation to any particular solution. But this has to satisfy a condition. And this has to be, it's not arbitrary. This has to have a limit as well that is non-zero, that depends on this other limit. So basically what happens here is that yes, so you have some radiation field, you have some data f01 times the log of r plus f0, yeah, at null infinity. And then this corresponds to something that goes on in the interior. But the thing is that you can't arbitrarily prescribe. So the interior is determined by the limit of these guys as you go towards, what do you call it, I plus in relativity, as r minus t goes to infinity. But those guys are not independent. And that corresponds to that, really, in the interior, you're solving kind of an elliptic problem. So you can't arbitrarily prescribe those data. If you try to do it, you would get something that blows up at the origin. We will come back to that later on. So So the limit of this guy in the interior is determined by the limit of this guy. I guess it will come pretty soon. Okay, yeah, so now about the interior. And this is actually, I think, a very simple argument that shows that something has to happen in the interior. So you have this source term, and we guessed that there will be a homogeneous solution of degree -1 in the interior, or it will asymptotically approach that. That's our guess, right? So we prescribe that we want to look for a solution of this form in the interior. So therefore, the only thing we do is we scale the equation to something that would have a limit if this was true. So you just scale this equation is scale invariant. You just get you get a different n there, right? If you scale. So this n goes much faster. But you get the same equation, just a different n. You multiply n by a, and you also this parameter a is here. And you let a go to infinity. And what you see is that this guy converges to a distribution, a delta function. So the idea behind that is that if you have something that looks like a times n, the wrong one, n of q, aq, and omega. What I claim is that this converges to a delta function of q, where n decays, right? N decays like n of q, omega is like at least 1 over q to the 1 plus epsilon. I claim that this converges to the delta function, right? Delta of q times the total integral of n of q omega dq. And this is easy to see, right? You just multiply by test function phi of q and integrate and change variables. You change variable aq, and it just becomes phi of q over a integral n of q omega q, right? So that converges to phi of 0 times the integral of n of q omega dq, which was what I claimed. Yeah, so the right-hand side here converges to a delta function on the lightcone. Q is r minus t, divided by r squared times n over omega, where n is the integral of this. And this, the right-hand side is homogeneous of degree -3 because the distribution delta function is homogeneous of degree -1. So the left-hand side has to be a solution which is homogeneous of degree -1, because when you take two derivatives, you decrease. And in fact, one can prove that it has this expansion as you approach the lightcone. Exactly this kind of logarithm plus this term. And this, in fact, follows from a formula I had in my thesis that actually it seems like no one has read my thesis, because this is a very useful formula, and which I'm happy about. But so you get this explicit form for the solution to this problem. And you see that the worst thing is if omega and sigma are in the same direction, so you replace this by n over omega, and then you just integrate, and you see that this comes out plus an error that is bounded. So you can actually calculate this n0 is exactly this integral here. So both of these are determined from this n. Both, as I said, both of those coefficients in the interior has to be determined from this n. Okay, so what have we proven so far? So we have proven that in the wave zone, when r is like t, we have this expansion, and in the interior we have this expansion. And now we don't have to be too smart to say that the limit of this, as r minus t go to the interior, minus infinity, should be equal to this, right? And the limit of this should be equal to that, as r minus t. So that's what we're claiming here. But at the same time, those two things are not independent. So it means that this limit has to be equal to this integral. Right. Now, what we want to do is we want to have a more accurate description of the solution, more detailed asymptotics, because the better asymptotics we have from infinity, the easier it is to solve the backward problem. If you have enough good asymptotics, you get an error term which decays very fast, and it's very easy to solve the backward problem. So we will now continue. So we had an approximate solution already, and we get an error that decays like 1 over r cubed that looks like this. And so now we propose a next expansion that pick up that error. And this was known that for the radiation field, you have a complete, I mean, without the logarithm, you had a complete expansion in powers of 1 over r squared. It was an analytic function, actually, if data are smooth in 1 over r squared. So we just do the same thing, but we add a log also, and you plug it in, and you see that you get the derivative of this faster argument on these two factors, and had to be equal, set them equal to these two factors, and the rest decays lower. And there's also, so you get the second order. And in the interior, you can also have a higher order expansion. In the interior, once you have these two coefficients, you plug it in and you get an equation for a homogeneous solution. So it's a simplified equation, and you can calculate these coefficients in terms of the earlier ones, and they satisfy certain relation. You can even do better. You can get the second order expansion in the interior of another term which decays like 1 over t squared, the next term in an expansion here. And it follows from the same argument. You just sort of scale to that time scale, so that with a squared instead, and you subtract off your delta function, and you see that that then converges to delta prime. And so you have to solve this problem, but actually the solution to this problem is just the time derivative of the previous problem. So you can use the same formula and take the time derivative. So that sort of gives a low order, next order term in this expansion. So we now have these expansions, and that in the wave zone and in the interior, and we have condition how to match the two. And doing that, we then prove a theorem. So the theorem is that assume, well, n is a given function, the source term, and the data for the sort of homogeneous part is not free. It has this h0 that can be any function almost that decays like, apart from one condition, q to minus 2. But then in the interior, it has to have this expansion. There has to be a limit, and also if you subtract off the limit, the next term has to decay at a certain rate. So these two functions are calculated from the source term. Now this is, it's arbitrary apart from one condition. And there is a condition, even if there was no source term, there is a condition. And this will be explained later on. Even just for the Friedlander's radiation field, that would be a condition. So we can explain that later on. Anyway, this equation has a solution with this expansion in the wave zone and this interior expansion plus the high order terms. So we solve this problem from infinity now. And the way we do that is that we construct an approximate solution. And with that, so we have a solution in the wave zone, and we have a solution in the interior, and we have to transition from one to the other. And then one could imagine transitioning maybe this is good enough. Yeah, so we have one solution, approximate phi rad in the wave zone, and we have one in the interior. And somehow one could try to transition when t minus r is like a constant, right? Or you could try to transition when r over t is like a constant different less than 1. But what actually works best is when this distance, t minus r, is like square root of r or square root of t. That just works. Something in between. And then this looks like a lot of calculation, but actually it's the main idea is that what happens is that you only need to estimate the difference of the two in the transition region. And this we have good estimate for. That's why you subtracted off all these terms, Q and so on. So these guys, we have the difference between the two, the solution in the wave zone and the interior solution, we have good estimate for because we subtracted off these terms from F0. So then you get an approximate solution such that phi, the real solution to our problem minus the approximate solution, is decaying like t to the minus 4, essentially. And that's enough, more than enough, to say that the error we estimated in L infinity is like t to the minus 2. So that's better than, I mean, we expect, phi looks like t to the minus 1, so the error is 1 power better. And that means that it's very easy now to, you can apply a very simple energy estimate to this equation to prove, to get the estimating energy norm. I mean, of course, the drawback with this argument is that we require more regularity of data at infinity than we get back for the solution, because somehow you throw the error into the right-hand side. Okay, yeah, so I wanted to explain what happens with, so this is the presumably the proof of Friedlander that you can calculate the radiation field from the radon transform of initial data and its derivative. So the radon transform is integral of initial data over hyperplanes. But if you look at that, you see that the integral of F0 dq has to be independent of the angle, because if you integrate this with respect to q, it becomes the integral of y everywhere, right? And that doesn't depend on the angle. So there is a condition on the radiation field already for the homogeneous equation, and that's the condition we had. Right. What is this? Yes, now we turn to the exterior problem, where we post data in the exterior. And we just actually decided to look at the homogeneous equation. So we don't have anything on the right-hand side. I can use that one, actually. We have initial data here that decays like 1 over r. And we don't have a right-hand side, so we solve box phi equal to 0. And then what we discover is that, well, several things, but that we actually, with data like this, we can get the same sort of logarithmic behavior as approach the lightcone as if you had a source. So that also has to be matched to, so if you have slowly decaying data, you will get something that's slowly decaying in the interior, which is not so surprising. But what was kind of surprising was that you actually can get exactly the same logarithm on the light cone as if you have a right-hand side. So inside you can't really know if the solution came from initial data or if it came from a source term. Right. So this is what we will do next. But what I will get to here, and this is what takes me to Func, is that we can, in the exterior, well, what we had was that we have a solution in the interior, we have a solution at the light cone that looks like, function of omega divided by r times ln t r over t minus r, plus another function over r. This is what we have close to the light cone. And we could match that to an interior solution. But now we want to match it to a solution outside, because we don't want to solve the forward problem. We want to solve the problem from infinity. But then we found a problem with that, which is that if we know that the solution looks like that, we don't know if it corresponds to initial data. We know initial data, well, we can prove that initial data that looks like this lead to something like this. But we couldn't prove that for any coefficient here, that corresponds to initial data that decay like 1 over r. And in fact, it wasn't obvious, right? Because in the interior, these were dependent on each other. So it wasn't obvious that those were free. But anyway, so this is what we were working on. And it actually took us some time, right, to figure that out. That was the main part of it. Took us maybe at least a year, right, to figure it out. So anyway, you can show that the solution for the forward problem, you can find similar formulas for that, which we calculated. So you can actually show that you get this logarithm. I can turn this off now. You can show that you get it follows from this formula. Okay, this formula follows from the fundamental solution. Some manipulation with it. You would have to read the paper, I guess, to understand this. But make a long story short, you can prove that you get this kind of expansion from initial data of exactly this form. So that's good news. But we wanted to go from infinity backwards, right? So we want to go from this kind of expansion for arbitrary coefficient, we thought, unless there was a condition, to initial data. And that's when we looked. Well, we figured that the thing is that the map from initial data here to these functions here, it's not the same n, right? So there's a complicated map. And it's something like the Radon transform, but it's not the Radon transform. And it's the integral of the sphere, so we searched on the web and for spherical Radon transform. And the following came up, something called the Func transform. So what it is the following. Okay, this is good. So if you have the sphere, and say that you have, take a direction, omega, and you integrate the function on the sphere on the great circle perpendicular to omega. And say that you know what that is for any omega. Do you know what function you started with? That's the question, right? And this transform is called the Func transform. And the question was that, is this one invertible? And first of all, it's not, right? Because if you have an odd function, this would vanish. So it would be invertible only on even function. And then, yeah, so Func was, that's the interesting thing. So Func was actually So he was a professor in Vienna, and he came up with this transform. And I think he had a proof of that it was invertible. And then Victor Gillerman worked on it, and Helgason worked on it. But what really solved the problem for us, it wasn't just the Funk transform, but the other transform comes up. For instance, this term that is called the Gank transform. And there were two more transforms like that, inverses to these two. And anyway, this paper, they proved that they are all invertible. Well, there was some work reducing it to those transforms. But they proved actually that those four transforms that we finally reduced it to are invertible on even respective odd functions. So there are four different transforms. You have to divide up the data in even and odd and show that those are invertible. But basically it worked in the end. And right. Oh, then we can also do low order when you have something that decays like one order more, which we also wanted to do, and you can solve that problem. And then we get this theorem here, which says that, so this is for the homogeneous equation now. And here we have these tails, a constant that goes to a constant and a 1 over q term. And there are certain conditions between them. Yeah, so those are all given. So those are free to give. But there's one of them that is not. Any interior is determined. Yeah, okay, so this M0 interior is determined by M0 exterior up to a constant. And this N0 interior has to be related to N in this way. Anyway, so then we can prove that you have the same kind of solution for the homogeneous equation with the same kind of logarithmic term here. And I believe it's related something to the, to Bondis-Maslow's law somehow, that you have the right-hand side, the source term enters into Bondis-Maslow's law and somehow canceled the mass from initial data. But I haven't worked that out. Okay, let's see. There's some more points here. Oh yeah, so Friedlander, and people thought that he sort of said that he could generalize his theorem to when you just have H1 data. And he proved that if you take the time derivative of phi and call that G0, that in L2 norm is determined by the H1 norm of initial data. So that seemed to imply that there is a map, right, between the radiation field and the initial data that doesn't even lose regularity. And that looked all well, but the thing is that it's just for the time derivative. And it's consistent with what we do, because if you take the time derivative, you get rid of this log term. Right? Well, it becomes 1 over t minus r, so it decays more. So it doesn't show up to the same extent as the leading order terms. Oh, and then you can apply this kind of method to other problems. The point, so here is a problem I did with my student, where you couple, and people have studied, in the audience have studied in this problem, where you couple the wave equation to a Klein-Gordon equation. But then you know that for a Klein-Gordon equation, the solution doesn't behave like a solution of the wave equation. It decays. It decays much faster, particularly along the lightcone. So there's nothing at null infinity for the Klein-Gordon, whereas in the interior solution to the Klein-Gordon looks essentially like a function of x over t divided by t to the 3/2, I think, times the phase. But that works fine because those are the kind of homogeneous solutions we look like in the interior. So it's natural to use this kind of method to match the behavior in the wave zone to the behavior in the interior. So this kind of method works for when you combine these two. And finally, what more did I want to say? Yeah, and you get some asymptotic system, asymptotic expansions for these solutions. So finally, I just want to go over some related problems mentioned. The first asymptotics for Einstein I proved, and then together with my student we looked at, and Kim Candy, we looked at asymptotics for Maxwell-Klein-Gordon. And the previous level, asymptotic for nonlinear Klein-Gordon and nonlinear Schrödinger, Delors had proven that. And we made a simpler proof in a special case with Avi-Sofer, and later on with Lerman, Sofer, and Schlag also. But with Avi, we also made scattering. So we started with those kind of data from infinity, and I guess that was the first paper where we did this. But this is just for one-dimensional Klein-Gordon, where it was easier. Either Klein-Gordon or Schrödinger, and solve backward. And then there's several other results here. Oh yeah, most important, Wang, student of Melrose, proved scattering for Einstein, but in 4 dimensions. So, and it didn't work in 3 dimensions. So that's a problem we are working on now. Try to do scattering for Einstein. And I think she had problem exactly with these things going on in the interior. Yeah, and you, student of Daniel, proved scattering for quasi-linear models from infinity. And my student, Lily Herb, proved scattering for Maxwell-Klein-Gordon with data at infinity. And then my other student now proved it with non-zero mass recently. This is what I have to say.